Okay, so let's start talking about seminorms from this lecture onwards. So, seminorms. So, what all we had discussed till now are the concepts of how to introduce topological, how to define topological vector spaces, the necessary properties, their separating properties, and the properties of the different topological and vector aspects of it. Then we discussed about its convexity, its local behaviors, bounded linear functionals on it, metrization and boundedness, right? These are the things which we have already done, and now we start talking about seminorms. Okay, and from seminorms we would be somewhat tending to the notions of local convexity, that what happens or what are the properties which we can study using seminorms, and one of the important aspects which come out to be local convexity, and one more aspect which we would be seeing is the notion of normability. Okay, normability. Rather, let's not get into there. Let's start with the definition of seminorms. Okay, and the definition of seminorms is exactly as we, one second, right? One second. Yeah, okay, so let's continue. Yeah, so let's start with the definition of seminorms. So, and there is obviously a concept which we already know about seminorms, and it is just mimicking out that. So, a seminorm on a vector space, and this is something to focus on. We are not yet, uh, concerned about the topological structure on it. Okay, x is a real valued function p on x such that number one, okay, yeah. So number one is that the obvious one, it obeys the triangle inequality. So p of x plus y is less than equals to p of x plus p of y, which should be quite obvious, right? And the other one should be that p of alpha times x is mod of alpha times p of x, and these happens for all x y coming from x and for all scalars alpha. Fine. Now this is called the, somewhere it's called the triangle inequality, but a more technical language would say it to be subadditivity. If you have studied measure theory, you will see that the outer measure obeys something which we called countable subadditivity, right? Yeah, let's not go there, but a more technical word to have this property is what we call subadditivity, right? Okay, now if I have a collection of these seminorms, if p is a collection of seminorms p on x such that, so I am applying a property on this collection such that for all x non-zero there exists some seminorm such that p of x is non-zero, then we say that p is a separating family, is a separating family. Okay, clear? Separating family of seminorms, or whatever, separating family of seminorms. Okay, fine. Now this is also a very important definition, that we say a in x, okay, or rather a in x, a convex set a in x is called absorbing if for all x, or rather if every x in x is in t times a for some t which I am specifically writing like this greater than 0. This is just, I mean to say that t depends on x. T depends on x. Okay, the thing is specifically like this. So yeah, so or rather let me do it in this way. Let's say this is your x, not your x, but the topological vector space x. This is a, and let's say this is some point small x. So what I try to say is that any arbitrary point you choose, you can just scale a by some t, and x will be contained there. Okay, and you can do it for every element in x. Okay, for every element in x, you will get some scaling factor t, right, which may or may not depend on the vector you are working with, but more or less that's the case. Fine. Okay, let me change the background. It's not looking good. Yeah, this is better. Fine. Okay. Okay, now this can be sort of immediately observed that every neighborhood of the origin is absorbing, right? This comes out exactly from the local behavior of the of any topological vector space. So an immediate example would be okay, one more thing I should be making here specific, that once we have defined the notion of a seminorm, after that whatever we have discussed, you can even consider the definition of the separating family as well to be included, assuming x to be a topological vector space. Though we are not concerned about the topology anywhere here, but since we are discussing topological vector spaces, and these definitions will work, obviously will go well whenever we require a topology here, right? We'll see that that's the goal of this part of seminorms, that we will see that these seminorms will behave, how they behave with the topological behaviors or the topological properties of the topological vector space. So every neighborhood of the origin is absorbing, and in fact something more you can see, that every absorbing set will contain the origin. You can try and prove it out, or you can in fact justify it. It just needs justification, that every absorbing set, and it's a very lame justification, contains the origin. Okay, fine, right. Okay. Yeah, now we define a very important aspect, or a very important tool, which will come out to be of great use a bit later though, which is called the Minkowski's functional. The Minkowski's functional, which we define like this. So mu a of x is, okay, A is an absorbing set. A is an absorbing set. Why do we require this? We will see. Okay, so mu a of x will be defined as the infimum of all those scaling factors t, such that t inverse x is in A, or x is in t a, whatever. Okay, x is in x. Fine. Okay, sorry, this is in, I am taking infimums, right? Yeah. Okay. So now why do I require A to be absorbing? So that this infimum exists finitely, right? So since A is absorbing, I know that for every x in capital X, there exists some scaling factor such that x is in Ta. So since A is absorbing, this mu A of x, this infimum exists finitely. Fine. Right? And we will see that this in fact mimics out a seminorm. Okay, this will mimic out a seminorm, and this will go very well with a seminorm. In fact, this will itself come out to be a seminorm, which we will be seeing later. Okay, mimic a seminorm. Okay, and this seminorm will actually withhold some very important properties regarding the topology of the space. Okay, these are the aspects which we will be seeing later, but more or less this is the goal of studying this part. Okay. Okay, fine. uh, yeah, so let us study a few important properties of seminorms. Okay, more or less our tools are done, right? Won't need any more tools. Properties of seminorms. Okay, one, or rather let me just be a bit precise. Okay, so let P be a seminorm on a topological vector space X, or you can just simply go with a vector space as well, but still let's be it a topological vector space. Number one is that the evaluation at the origin is just 0. Okay, you need to be precise here. This is just numerical 0. This is your origin, right? Because the seminorm is a real valued function, if you recall, right? And its domain is the topological vector space. Fine, recall it, right? Fine. Sorry. Number two, mod of px minus py. The absolute value is obviously well defined since we are working inside the reals. It is less than equals to p of x minus y. Number three, p of x is greater than equal to 0. Okay, so we have a non-negativeness as well. Non-negative definiteness is something what it's called, non-negative definiteness. Like norms have positive definiteness. Number four is that if you consider this set X such that p of x is less than 1, sorry, p of x is exactly equal to 0, then this forms a subspace. Subspace of what? Subspace of x, obviously. And number 5, that if you choose all the x such that p of x is less than 1, then this forms a convex, balanced, absorbing, and in this case your p will exactly come out to be the the value mu b, right? The value of the Minkowski's functional. Okay, yeah. So let's see the proof of these one by one. Okay, proof. Okay, yeah, I'm a bit sick. That's why, I'm coughing and drinking like that. Drinking water, obviously. Proof 1. Okay, now this is quite obvious. See, you have p of alpha x equals to mod of alpha times p of x, right? This is inside R. Okay, so what is p of 0? It is p of the 0 scalar times x being any arbitrary vector. You can write it as 0 times p of x, and it is 0. Fine. Yeah, now this in the proof of 2 you can just mimic the proof of the the what we call the reverse triangle inequality in case of the reals. That is, you can write p of x as p of x minus y plus y, which is less than equals to p of x minus y plus p of y. So just take p of y on the left hand side. So p of x minus p of y is less than equals to p of x minus y. Okay, and in a similar way you can write p of y as p of y minus x plus x, which is less than or equals to p of y minus x plus p of x. But then p of y minus x, this is nothing but p of x minus y, right? Because I can choose minus 1 common outside, it will come with its absolute value, so it's just 1. So this is exactly equal to p of x minus y. plus p of x. Again take p of x to the left hand side, so we'll get p of y minus p of x. It is still less than equals to p of x minus y. So from the here and here it's obvious that mod of p of y minus p of x is less than equals to p of x minus y. Fine, right? Okay, good enough. Let's move on to the next proof. Okay, I think I need to go and take my medicine, so just a minute, just a minute. Yeah, fine. Okay, okay. Okay, yeah, so the reverse triangle inequality is proved. Okay, let's check out the next part. Okay, so what was the next part given? Number C was given to be px is greater than equal to 0. Okay, yeah, this is quite obvious, right? How it is quite obvious? What do we have here? Okay, yeah, so can we make out something from here? Yeah, okay, we can do one thing. We can just choose y to be equal to 0, right? Not here exactly, sorry, that's a very misleading statement. Okay, let me write it in part C. See, what we have is this, right? This is less than equals to p of x minus y. So therefore if y is equal to 0, then we have mod px is less than equals to px, and this is something greater than equal to 0. Yeah, we have it, right? Okay, now let's move on. Okay, part D is very easy. Just take this as an exercise. It's very easy. Just choose out two values x and y, both giving 0, and then just take any arbitrary linear combination and then use the properties of seminorms to see that it will still be 0. Let us move on to part E. Now balancedness is obvious, right? Because if x is in B, then p of x is less than 1. Now if alpha is a scalar such that mod of alpha is less than 1, then p of alpha x, this will be equal to mod of alpha times p of x, and this will still be less than 1, right? So what does that mean? That means that alpha x will be inside B, and that this will happen for any scalar which satisfies this. Therefore B is absorbing by its definition itself, by the definition of being, sorry, not absorbing, balanced, sorry. Yeah, so balancedness is trivial, balanced. Fine. What can we say about the convexity? Okay, so if x and y come from B and 0 less than t less than 1, you can just take this linear combination p of tx plus 1 minus t times y, and then just break it out, right? So this will be less than or equals to t times p of x plus 1 minus t times p of y, and this will still be less than 1, right? So it's convex, obviously, right? What more can we say? Okay, what more can we say? Okay. Yeah. Okay. What had to be proved next? B was absorbing also, right? Something of that sort. Okay, yeah, I need to show B is absorbing, right? How do we do that? Okay, so let x be in X. Suppose if S is equal to Px, not P. Okay, so let x be greater than Px. Fine. Then what is P of S inverse X? Right. So this will be S inverse times Px. Okay, S is greater than 0. I'm assuming S is greater than 0. but then what do we have? So from here we have S inverse times Px is less than 1, so this is less than 1, right? That means S inverse Px is in B, right? So this means B is absorbing. Fine, okay. And why is it absorbing? Because X was chosen to be arbitrary. Yeah, fine. And you can also immediately see that this S somewhat depends on X, right? It depends on how we are evaluating X at using the seminorm, right? Now observe this. Now if 0 is less than t less than equals to P of X, then if 0 is less than t less than equals to P of X, then P of T inverse X, this is greater than or equal to 1, right? You can just use the property of the seminorms here, okay, which implies that T inverse X is not in B. But then what does this imply? This implies that P of X is less than equals to the Minkowski's functional at X, right? Fine, clear? And which immediately implies that mu B is equals to P. Got it? Okay. Fine, fine enough. Okay. Yeah. So now let us examine. Yeah. So we did this. Just go through the proof and just fill in the gaps wherever you require it. Okay. That's the best way of learning though. Okay. So fill in the gaps wherever required. Fine. It's a very easy case to observe. Okay. Yeah. Let's go to the next page. And now we want to examine the Minkowski's linear functional. Okay. So examine the Minkowski's linear function. Okay. Yeah, I will be using this abbreviated form. Okay, MLF, sorry. Okay. Yeah. So suppose A is a convex absorbing set, okay, in a vector space X. Fine. Then the following properties holds, and here we can see that it actually mimics a seminorm, or actually itself is a seminorm. Okay. Then A, that mu A of X plus Y is less than equals to mu A of X plus mu A of Y, and typically these proofs just require the definition of infimum and nothing else. Okay, it is that much trivial. Okay, and that mu A of Tx is mod T times mu A of X, or rather just T times mu A of X, but T is greater than 0. T is greater than or equal to 0. Number C, if mu A is if A is balanced, then mu A is a seminorm. Number D, if B is this following collection: 1, and let's say C is this collection, mu of X is less than or equal to 1, then we have the following inclusion, that is B is contained in A, is contained in C, and mu B is exactly equal to mu A is exactly equal to mu C. Okay, yeah, fine. So just try out the proof yourself for now. Try out, and we will come up with the proof in the next lecture. So meet you guys in the next lecture.